In this module, we'll look at the RC circuit. We'll look at charging and discharging a capacitor. So if we look at a discharged capacitor, we could look at this switch with this circuit that has a two-pole switch. So this two-pole switch, the capacitor and resistor series combination can either be connected to position A and be connected to an EMF device to charge the capacitor, or it can be connected to position B and connected back down through ground, and the capacitor will discharge through the resistor, and the charge on its plates will recombine. So let's think of it, if it was in position B here, then any charge that was on the plates of the capacitor would travel in the form of current, and that charge would then come through the circuit and recombine, and eventually there'll be no charge left to move, so the potential difference across the capacitor, VC, would equal QC, and since Q equals 0, would equal 0 times Q. So the potential difference across the capacitor will be 0, the charge on the plates of the capacitor will be 0, and that's our completely discharged capacitor. So if we start in that state where the capacitor is completely discharged, and then we switch our two-pole switch to position A and allow our RC series combination to be connected to the EMF device, current will flow from the EMF device to the top plate of the capacitor. That charge will accumulate on the top plate of the capacitor. Through the polarization effect, we'll get a negative charge on the bottom plate of the capacitor, and we will get polarization along this conductor as well, and we'll have a current flowing through this circuit until an equilibrium is reached. That equilibrium will have to do with the capacitance of the capacitor, where our VC will equal to our EMF of the EMF device, and that will equal to our charge on the capacitor divided by the capacitance. And we're at equilibrium, and charge will no longer flow. So what we want to look at is what happens between the time that the current starts to flow and our current becomes 0 and we have a completely charged capacitor. We can use our loop equation to analyze what's happening as the capacitor is charging. Our loop equation, if we start in the lower left corner, we increase in the direction of the EMF device, so we have positive EMF. We decrease in the direction of current flowing across the resistor, so we have a minus IR, that's our Ohm's law. And then we decrease in the direction of the voltage across the capacitor. Voltage across the capacitor is the charge at that given time divided by the capacitance. And we know, in fact, that that's a decrease. It's written here as plus or minus VC. It's a decrease. Our capacitor rule, if we're going from the direction of lower potential to higher potential, then we'll have a positive Q over C. If we're going in the direction from higher potential to lower potential, we have a negative Q over C. We know the positive side of the potential is related to the positive charge. So if we continue with our loop equation, we end up with an equation, but we have one equation and we have these two unknowns, or one unknown of the Q, the charge on the capacitor, and the other unknown I, the current that's flowing in the circuit. But we do know I in terms of Q. We know we have our relationship that I, our current, is equal to the rate that charge is changing with time. So we have a first order linear differential equation that we can rearrange in terms, in this equation of Q, we have our dQ dt plus our 1 over RC times Q is equal to something that's not in terms of the charge, our EMF divided by the resistance. And you can see each of these terms then must be have the unit of amperes, since dQ dt, that's our definition of current, that has a unit of amps. Our voltage divided by resistance, that's our Ohm's law, that has a unit of current. So our charge divided by the resistance times the capacitance must also have a unit of current. So now we have to solve this linear differential equation. We'll look at, there's a number of different ways to solve this simple differential equation. We'll look at the particular solution and the complementary solution. If we look at our particular solution here, what that means is that is the solution that hangs around once all the time-dependent variations die out. So in our case, we call that's due to the forced response. Our forced response is that's due to the EMF device. The EMF is some other energy source other than the electrical source, and that's what is going to hang around after the electric field dies out, and we build up an electric field between the plates of the capacitor. So that's also called our forced response of our circuit, and we know that's going to be equal to the capacitance times the EMF. That's our formula, that Q is equal to CV. Once we're at equilibrium, that V is going to be the voltage across the capacitor, will be the EMF, and our current will be 0. So that's our particular solution. Our complementary solution is this constant K times e to the negative AT. That's our complementary solution, or the natural or unforced response to the circuit. The nature of the circuit, which has to do with the electrical response of the circuit, has to do with the resistor and the capacitor in the circuit. So we want to know what is A and what is K. Well, if we just look at this term for a moment, A is raising A times T to an exponential. The unit that which we raise an exponential to, it must be unitless. So if T has a unit of seconds, A must have a unit of 1/second per second. So that's a type of a frequency. And we know also that this is a charge equation, so our K must be some type of a charge. So for this circuit, without solving for it, we'll go by experience, that A must be 1/RC, or 1/tau, where RC is our time constant. So tau is a time constant for the circuit. For an RC circuit, that is equal to RC, the equivalent resistance and the equivalent capacitance in the circuit. Our K then, we can be found using our initial conditions. So the charge, when we first start up, at T is equal to 0, that charge is equal to 0. So we start with a discharged capacitor, so there's no charge on the plates of the capacitor. So if Q is equal to 0 at that time, then we can say 0, right? Set that equal to 0. 0 is equal to CE times K e to the negative T over tau, where tau is our RC. And then our K must be equal to negative C times E. And again, that's going to have a unit of charge, since Q is equal to CV. So our charging equation becomes Q of T is equal to the capacitance times the EMF device minus capacitance times the EMF device e to the negative T over tau, or we can write that as capacitance times the EMF device times 1 minus e to the negative T over tau, where again our tau is equal to RC. So our after, when T goes to infinity, at T goes to infinity, after a very long time, this term, e to the negative infinity, is 0. This term goes to 0. So the charge on the plates of the capacitor is the capacitance times the voltage across the EMF device. At T is equal to 0, e to the negative 0, that's 1. So 1 minus 1 gives us a 0. We have an initial charge of 0. So we've satisfied both our initial conditions and our final conditions with the solution to our differential equation, which we found using our experience of the form of our natural response being some damped exponential, and knowing we used from experience the time constant. We found that tau for an RC circuit is equal to the equivalent resistance, the equivalent capacitance in the circuit. Let's look at our charging equation again. Our charging equation is a function of time. What happens with that is increases over time from 0 to our capacitance times the voltage across the EMF device, not linearly, but in this form of 1 minus e to the negative T over tau. So at after one time constant, e to the negative 1, we're at 63%, approximately 63%. So this would be about a 6.3, since this looks like it's 10, of our final charge on the plates of the capacitor. what's happening to the current spikes up initially from 0. It spikes up, in this case, to our EMF divided by that resistance, and then it decreases. It's our dq dt, so it's just E over R, which is a current, times e to the negative t over tau. So that decreases in this exponential fashion. And the voltage across the capacitor is the charge divided by the capacitance, so that's just our voltage times 1 minus e to the negative t over tau. So again, that capacitive time constant, RC, that's the time it takes for it to reach 63% of its final value. Our charging equation, our current in the loop, our voltage across the capacitor. These are all the important equations. If we look at this in terms of percentage, after one time constant, we're at 63.2%, two time constants, 6.5, 95% within three time constants. So you can plug these numbers to get them for yourself. Let's look at our discharging capacitor. If we move the switch once it's charged from A down to B, what the current's going to do, it's going to move away from the plate of the capacitor and it's going to recombine with the negative plate of the capacitor. We know that's the direction of the current, but we'll still use the sign convention of the passive capacitor. So our current flowing in the direction of the potential decrease across the capacitor. We'll show our current flowing in this direction, even though we know positive charge is going to be flowing in the opposite direction. And we'll solve this differential equation. Then we know the voltage across the resistor then, that plus the voltage across the capacitor. If we go this direction, VC plus VR must be equal to 0. So our R dq dt, that's our Ri, plus Q over C must be equal to 0. And we have our first order differential equation where a particular solution in this case is equal to 0. So our particular solution is 0 at times equal to infinity. We have the same time constant, so our frequency A is 1 over RC. When we use our initial conditions to solve for K, we get that our Q of 0 is C times the EMF, K e to the negative t over RC, so our K is just equal to C times that EMF voltage. So when we go to solve this differential equation, we get the charge is our Q naught, that initial charge, times e to the negative t over tau, where Q naught in this case is going to be the capacitance times the voltage across the EMF device. And our current is the derivative of that, so that's where we get the negative Q naught over RC e to the negative t over tau. So we have defined our current flowing in the direction of potential decrease, so we could use it I is equal to dq dt. And we see that the positive current is actually flowing away from the positive charged plate as we would expect. So if we look at this case of our discharging equation and the voltage across the capacitor when we're in fact discharging, if we relative to a 1, we're decreasing after half of the time constant, we've decreased 61%. After one time constant, we've decreased to where there's only 37% of the original charge on the plates or the original voltage across the plates. These two are directly proportional to each other. The current, if we look at current flowing in this direction in terms of passive sign convention, our current is going to be negative. And so we would have to start down here, and it's going to decrease up to 0 in the same form. If we look at our negative current, then it's going to flow, it'll all have the same form. So that's our RC circuits. We'll practice these in class.